The Aluminum Intensive Vehicle Program was a 2-year study to achieve implementation readiness for a high-volume stamped aluminum body structure. The AIV program emerged from a comprehensive comparison of 4 potential lightweight vehicle structures: stamped aluminum, aluminum space frame, composites, and steel space frame. This study concluded that stamped aluminum provides the greatest weight benefits, best suits Ford's manufacturing infrastructure, and is the only technology capable of high-volume production by the end of this decade. The AIV program was directed by a cross-functional steering team composed of executives from Alpha, Body and Assembly, Body Engineering, Car Product Development, Purchasing, and Research. The program was managed by a macro team with managers and chief engineers from those activities. Key issues are resolved by a series of micro teams, which combine the efforts of more than 150 engineers, scientists, and technicians representing virtually all areas of the company and selected suppliers. The program was funded at over $30 million, drawing primarily on the financial resources of Car Product Development and the Product of the Future Fund, with support from Vehicle Operations, Technical Affairs, and ALCAN. These implementation readiness studies have been divided into 2 categories. Product issues are being addressed by building and testing 20 aluminum sables to enable a direct comparison to a production steel car. Manufacturing issues are being resolved by an extensive array of statistically designed experiments, or DOEs, followed by a macro-scale manufacturing prove-out of key representative vehicle structure subassemblies. The result, as you'll see in the next few minutes, is an aluminum body structure that will be ready for high-volume implementation before the year 2000. The road to implementation readiness began with the Vehicle Design and Build program. The Sable was selected for several reasons. It's a high-volume mid-size car, which can be scaled up or down to meet future program needs. Also, aluminum hoods, fenders, and deck lids from DN101 pilots could be used. Finally, a wealth of analytical and test data were available from the 1992 DN5 redesign and DN101 body structure upgrades. Key to the success of the design process was the more than 12 man-years of analysis performed in 6 months to understand safety, durability, and NVH of the aluminum body structure. The bodies in white and finished vehicles were assembled at the New Model Programs Development Center. This pilot plant build process provided valuable insight into aluminum tooling design, stamping, and assembly issues. 14 months after the program started, the first AIV rolled off the assembly line. The AIV cars were tested to the same standards as production cars. Key tests critical to putting a car on the road were selected. Let's look at some results. The AIV performed well in a 35-mile-per-hour front barrier crash on the first test. Driver head injury, or HIC, was well below both federal and Ford standards. Chest acceleration and femur loads for the AIV occupants were better than those recorded for the Mercedes 300, reported to be one of the safest cars in the world. These results are a tribute not only to the design, analysis, and build teams, but also to the very strong CAE capability that Ford has in safety analysis. The AIV was also tested in a 35-mile-per-hour rear-moving barrier crash with no fuel leakage. Other safety tests will include roof crush, side impact, and seatbelt anchorage. Rough road durability testing is also underway. To date, the AIV has completed nearly 200 cycles of the Michigan Proving Grounds with no aluminum-related failures. This corresponds to 50,000 miles of severe use. Testing will continue to assess durability beyond 100,000 miles. The AIV design incorporates structural adhesive to supplement the spot welds in joints critical for durability. Durability testing is also underway for an AIV built without structural adhesive, and one with about 20% of the spot welds deleted. Other critical issues in structural design are noise, vibration, and harshness, or NVH. An extensive experimental program has established that aluminum cars can be as rigid and quiet as steel cars. In bending stiffness, the aluminum body approaches the steel sable, while in torsional stiffness, the AIV exceeded the steel car by over 40%. Structural adhesive present in the AIV contributes to this improvement. In objective sound testing, the AIV was essentially equivalent to the production steel cars for road noise, wind noise, and powertrain noise. These data and the higher modal frequencies inherent in a car with lower mass and similar stiffness indicate that an aluminum car may have better NVH potential than a steel car. To test this hypothesis, an AIV2 design will be built, which incorporates several structural upgrades planned for the DN101. Another advantage of aluminum is corrosion resistance. Testing at the Ford Proving Grounds is confirming this. Although the results will not be available until early 1994, there's high confidence based on extensive field data from many years' production of aluminum hoods, bumpers, and other components. This experience has led to design and use of proper fasteners and correct alloys. Collision repair, another important product issue, is being addressed by a team which includes representatives from the insurance and repair industry. Supported by experimental data, the team concluded that basic repair procedures used on steel will work for aluminum body structures. Training procedures and welding equipment are being developed to support future high-volume aluminum cars. The second and most challenging component of the AIV program is manufacturing implementation readiness. Manufacturing issues were approached in a unique way. The program started with a system developed by Alcan over an 8-year period, which includes aluminum alloys, pretreatment, forming lubricant, and adhesive, all compatible with one another. The micro teams then went into the laboratory to collect data through an exhaustive set of DOEs. Although some minor issues remain, these experiments laid the groundwork for a robust production process, which was confirmed by a macro-scale manufacturing prove-out. The macro prove-out was performed with Progressive Tool, Ford's body shop supplier. In it, 150 sets of 2 key structural subassemblies were produced in 5 groups of 30 each. The 2 subassemblies, the front apron side member and the rear quarter panel, contain many of the manufacturing complexities found in an entire body. The macro results are best expressed in the form of potential process capability, or PPK. Ford requires most production processes to have a capability greater than 1.33. The macro prove-out established that the welding and adhesive bonding processes have a potential capability of greater than 1.67. The macro prove-out provided a great deal of information about how to build aluminum bodies in high volume, but it would not have been a success without the extensive micro experiments on welding and adhesive bonding. More than 500,000 spot welds were made in evaluating the Alcan process. This analysis and testing has provided basic information about the characteristics of aluminum welds. The adhesive bonding studies looked at 2 issues. First, the long-term properties of bonded joints were established through laboratory testing at Ford and suppliers. Simultaneously, manufacturing concerns, such as dispensing and curing characteristics, were resolved. The adhesive must be cured prior to painting to prevent washout during pre-paint cleaning operations. Therefore, a new body shop oven is required. High-volume designs, such as this turbulator model, may enable shorter cycle times and smaller ovens. A follow-up study is underway to assess alternative methods of curing the adhesive which do not require a body shop oven and could potentially save the $6 million investment. Ford is the industry leader in stamping aluminum, producing over 350,000 aluminum hoods per year. Additional stamping trials for the AIV were performed to establish feasibility for the entire body structure. The result is a series of guidelines which help to bridge the gap between design and manufacturing. Other manufacturing issues, such as paint and sealing, were addressed by laboratory testing and by painting 3 bodies at the Atlanta assembly plant. A study is underway to optimize the coating process for an all-aluminum car. It may be possible to eliminate phosphate and electrocoat, which are required for corrosion protection of steel vehicles. This would result in substantial savings in facilities and variable costs. What are the benefits of an AIV? The primary driver for this program was, of course, weight reduction, significant weight reduction. By converting the body structure and closures to aluminum, the weight of other systems in the vehicle can also be reduced. The result is a Sable which weighs nearly 700 pounds less than the present steel car. That's a 22% overall savings. It drops the Sable 6 emissions test weight classes from 3,500 to 2,750. Here's how the weight savings are broken down. The body structure itself is 46% lighter than steel, which saves 275 pounds. The closures are 52% lighter, saving 114 pounds. And the rest of the vehicle is 12% lighter, which saves 295 pounds. These weight savings contribute to substantial fuel economy and performance gains. For equivalent powertrain technology, every 10% reduction in weight produces about a 6% increase in fuel economy with similar gradability and improved 0 to 60 times. This has been confirmed by subjective testing, in which AIVs have scored higher than steel cars in overall performance feel. Another benefit of AIV is emissions reduction. Lighter cars with smaller engines will make it easier and less costly to achieve future emission standards. There you have it. Product and manufacturing implementation readiness in 2 years. An aluminum body structure ready for high-volume production before the end of the decade. Ford now has an understanding of aluminum body construction methods that far exceeds the competition. The AIV was accomplished by dedicated and empowered teams with a single focused goal: implementation readiness. Success was achieved by taking a total systems approach, involving all parts of the company and making maximum use of our computer-aided engineering capability. The program serves as a model for future advanced development programs.